Welcome back to CS264A Automated Reasoning. And today we're going to be talking about a new application which is known as model-based diagnosis. This is one of the topics that were actually tackled by AI quite a long ago, and particularly in the 80s, it is to some extent considered to be a well understood problem, but it's actually interesting because it exemplifies something more general, which is trying to find out what happened when things go wrong. And even though we're going to be talking about it in the context of diagnosing systems, it also applies to more general things like trying to find contradictions in beliefs. In fact, this topic which is considered to some extent solved initially, became more relevant recently because the underlying techniques and concepts are now playing a role in explainability and explaining for example, the decisions of machine learning systems, a subject that we're going to be talking about during the next lecture. So what we will discuss today, even though it will be done in the context of model-based diagnosis, will actually find uses next. Now, this topic is also traditionally, when it was formulated, it was very strongly tied to two representations that we talked about in passing, and that is the prime implicant and prime implicate representations of Boolean formulas. We just mentioned them and we said we're going to talk about them later in the context of applications. So in fact, today, we will start with these two representations to talk about them in some detail. Now, initially, model-based diagnosis was very tied to these notions, both computationally and semantically. Later, the tie was only semantical, and we found better ways to handle computational things, and we'll see that today. But semantically, they're still very relevant. And in fact, those notions in particular, prime implicants, now are playing a major role in explaining machine learning systems. So that's why we will go over them first and make sure we understand them, because we're going to use them next time when we talk about explainability. So again, the plan for today is initially we will discuss prime implicate and prime implicant representations and then talk about model-based diagnosis after that. All right, I'm going to go ahead and head to the whiteboard now so we can get started. All right, so what we'll do is start with prime implicant and implicates, and I'm actually going to start with a clean page here so that we can have more landscape. And these two notions are pretty influential, and they're related, they're dual to each other. So I'm going to try to explain them side by side, and starting with the very basics, because you need to be really comfortable with these notions. They come up all the time. We'll start with prime implicates first. And here we're going to be preparing the grounds by talking about some notions related to clauses and terms, because prime implicates are basically clauses, and prime implicants end up being terms. So before we even give the definitions of these things, we need to be familiar with some key notions related to clauses and terms. So the first thing here is the definition of when a clause C1 subsumes another clause C2. Right? And let's take an example of that, because this notion of subsumption is very key in these definitions. So let's say I have this clause A or not B, and then I have this clause A or not B or C, and let's call this C1 and this C2. And in this case, we will say that clause 1 subsumes C2 intuitively. It means that if I have this guy, there is no need for that particular guy, because this is implied by that. And that's precisely when basically C1 implies C2 or entails C2, all right? You can see that intuitively. If I tell you A or not B, then there's no point for this. This is saying A or not B or C, which is weaker than that. When we represent clauses using sets, like what we've been doing, then this ends up being simply set subsumption or set inclusion. So that's what's going on. So you need to visualize this. Anytime I say a clause subsumes another, you need to think of this being a subset of that. Now, this typically comes in the context of CNF representation. So I may have a CNF that looks like this, where I have A or B, that's one clause, and this is another clause, and this is here a third clause. And what we have here is that one of these clauses is subsumed by another, right? So this guy here, the first one, does subsumes that. And in that case, we will just go ahead and say, remove the subsumed clause. That's basically where things come up, is that I end up removing subsumed clauses. And in connection to this, I'll remind you of the principle of resolution, which will play a role again later. And if you recall what resolution was, is that we had some clause of the form alpha or x, and another clause that was beta or not x, and we went ahead and resolved on the variable x, and in that case we generated this particular clause alpha or beta, right? It's an inference rule typically used on CNFs, and it allows me to go and add more clauses to the CNFs which are implied. Okay, you'll see the relevance of this in just a little bit. And just going with some example here, if we have A or B as one of our clauses, and the other clauses is not B or C, and then the third is not C or D, then you can apply resolution in this case, for example, to these two guys, and I will get A or B as an inferred clause. And similarly, you can actually resolve these two guys and get not B or D. Okay, so this is quite familiar, but the main thing is you really need to be comfortable with this notion of subsumption. We're gonna use it quite a bit later. And now I'm gonna draw the corresponding picture for terms, which is probably not as familiar because we worked quite a bit with CNFs, and terms come up in the context of DNFs, and in a sense, for our purpose, particularly when we get to explanations later, prime implicants will play a major role. So this is something we need to further our intuition about. So we're talking about terms here, and terms basically, I should put here, is a conjunction of literals. And of course, we know that a clause is a disjunction of literals. And then we have the notion of a term T1 subsumes term T2, right? So now we have the notion of subsumption again. And let me put actually two of them here as an example. And the first is A, not A and C, and the other is not A and B and C. So let's see, these are the two terms. In this particular case, I'm going to call this one T1 and this guy T2. Let me ask you a question. If you had a DNF, and that DNF contained both of these guys. Remember, sorry, yes, a DNF. So a DNF is a disjunction of terms, right? It's a disjunction of terms. So you're gonna have this or dot, dot, dot. And if the intuition behind subsumption is that the subsumed term is not needed and could be dropped, in this case, which one of these two guys subsumes the other? Does T1 subsume T2 or the other way around? Okay, I'm getting conflicting answers here. Some people are saying drop T1 and some people are saying drop T2. Okay, let me give you the definition and we'll see what how we can argue for this intuitively. And in this particular case, actually, this guy subsumes that guy. So if I'm gonna use the notation for implications, it will actually be that basically T2 implies T1. All right. Now, this is now a little bit different or appears in the opposite direction to what we've seen for clauses. But if we actually use set notation, they'll end up being the same. So if I do represent this term as the set, this guy here, and I do represent this as the set, then it also ends up being subset inclusion, right? So in both cases, in a way, the shorter subsumes the longer. Now, why do things flip when I do it this way? Because this set is a conjunction and this set is a disjunction, right? So, okay, let's take an example and hopefully things will be clearer. So if you look at DNF in this case, and let's say this is our DNF, and we go ahead and write the following. We write X and Y, or X and Y and Z, or X and W, all right? So in this particular case, for this DNF, this guy can be dropped. This guy can be dropped in this particular case because this is subsumed by that. The easier way to think about it, which would be consistent between clauses and terms, is that the shorter, the smaller subset subsumes the larger set. Okay, in this case, this guy subsumed that. In this case, this guy subsumed that. And here I will remove it. All right. So one way to think about this is the following. The intuition here is the following. What does it mean to have this as a term? I'm telling you, this DNF is X and Y or da, 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 da. Anytime you have a term in a DNF, you can think of it as a partial variable instantiation that satisfies the formula. So the minute you see this, so you're saying that as long as I set X to true and Y to true, this formula is satisfied, okay? Now, what does this say? This says if X is true, Y is true, and Z is true, you can satisfy that formula. But isn't that implied by this, right? This is less restricting. This is saying, well, I just need X to be true and Y to be true, and I'm done. I can satisfy this. This is saying I want X to be true, Y to be true, and Z to be true, and I'll satisfy the formula. So you can see this is what this guy is saying is already basically covered by the first guy. And we will write a rule now that correspond to resolution that you can use on DNFs to add more terms, and then we're going to see how this is going to play a role later. So we always think about clauses, right, as things that follow. So when I write this, you're saying, oh, this knowledge base is saying that A or B must be true. Here, you think about it differently. You think about it, if this is saying that if X is true and Y is true, then this formula is satisfied. So let me show you here the corresponding rule to resolution, which we call consensus. And again, it will play a role in just a little bit when talking about prime implicant and prime implicants. And this says if you have a term that looks like this, and then you have another term that looks like that, so what happened here is one term that includes X and another term that include not X. So these are variables. Then you can add to the DNF the term alpha and beta. All right. You can think of it as an inference rule that allows you to add more terms to a DNF without changing its content. So if I had the following X and Y, or not Y and Z, or not Z and W, that's my DNF, then I can now go ahead and do resolution in this particular case. So here, sorry, I can do consensus. If you look at this term and that term, I have Y here and I have not Y there. That means I can go ahead and add another term, which is just X and Z. That doesn't change the logical content of this formula. And here's another opportunity for doing consensus on Z. I can add not Y and W. All right. So if you think of resolution as allowing us to add more clauses to a knowledge base without changing its logical content, consensus is an operation that allows us to add terms to a DNF without changing its logical content. Okay. So now we have the ingredients needed to define these notions of prime implicate and prime implicants. What is a prime implicate? And here we're talking about a knowledge base, and let's call this basically delta. And I want to talk about what is define a prime implicate of that particular delta. And this comes in two stages. First, we define the notion of an implicate. So an implicate of delta is nothing but a clause C that is implied by delta. That's it. Okay. So if a clause is implied by a knowledge base, I will say that it is an implicate of that knowledge base. And now we can define the notion of a prime implicate. And it's going to be simply an implicate of delta that is not subsumed by any other implicate. Okay, so let's take a concrete example in this particular case. If you have your knowledge base delta as, let's say, not A or B, and let's keep it simple in this case, and then I have not B or C. That's basically it. This is my knowledge base. So question, is not A or C, let's call it, is this an implicate of that knowledge base? This is a clause. It satisfies the first condition. Does it follow from this guy? And you should be able to show that this follows from that using resolution, right? If I resolve on B, I'm going to get this. So indeed, in this particular case, I do have that delta implies alpha. And in that particular case, basically alpha is an implicate. All right, so now let's take another guy, which is this guy, not A or C or D, right? So here we established that this is an implicate. And this is also an implicate. The question is any of these prime, right? Let's start with this guy, right? So this is also a clause that follows from the knowledge base. So I also have that delta implies beta, all right? So in both cases, these are both implicates. Question, is beta a prime implicate in this case? Remember what the definition, it is a prime implicate. If it's an implicate that is not subsumed by another clause, and people are saying no. And the reason is I do have another implicate that is shorter, that subsumes it. So this is basically here not prime. Now let me ask you another question. Is the first guy a prime implicate? Now, prime implicate, it has to be an implicate, we established that. And no subset of it. The only way you can shorten this is by either dropping C, and this way you get not A. Is not A implied by this? It's not. The other way is you can drop not A and get C. Is C implied by this? It's not. Of course, you can drop both and get a contradiction that's not implied. So actually, this ends up being a prime implicate in this case. So the short story is it is a clause that is implied by the knowledge base, and no strict subset of it is implied by the knowledge base. All right. And the main thing we want to do is, and now we're ready to talk about this notion of a PI representation or a prime implicate representation of a knowledge base. And this is effectively just a conjunction of all prime implicates of delta. Okay, that's the new representation that we talked about, and we called it the PI representation when we discussed the knowledge compilation map. It's simply, you take a knowledge base and you go ahead and compute all its prime implicates, that is, all clauses that follow from it, and those clauses are in a sense minimal. They cannot be shortened. And then you take their conjunction, and that would be the prime implicate representation. The main thing is, how do you actually compute such a representation? And there is a procedure for this. So you can do this by simply closing delta under resolution, then dropping subsumed clauses. So if I give you a knowledge base like this one, which is basically not A or B, and not B or C, and not C or D, and then I tell you, go ahead and represent this in prime implicate form, or PI, as a PI, then what you will do is you will apply all possible resolutions to this. And when you can no longer apply resolution, basically you throw away all of the subsumed clauses, and that's guaranteed to be the set of all prime implicates of the original knowledge base. So if you actually try to do a resolution here, you can do a bunch of them. You can do resolutions on B, so that gives you the clause not A or C. You can also do a resolution on C, and that gives you not B or D. Let's see, can we do any other resolutions in this case? So I did so far, I got this guy by resolving these two on B. I got this guy by resolving these two on C. Is there any other resolutions in this particular case that I can do? Okay, someone is saying I can resolve on B, these two guys, and I should be able to get not A or D. Any other resolutions that I can do in this particular case? There should be no more resolutions. Now, we lucked out in this case that when we did this, we didn't get any subsumed clauses. None of these clauses subsume the other. So in this case, basically, I have computed all prime implicates, and this would be a prime implicate representation of the original knowledge base. All right. I will mention two quick properties of this representations. And if you go to the knowledge compilation map paper that we distributed, you'll see all of the other properties it has. One of the main properties of this is that doing causal entailment is easy. We call that CE. This is when you're trying to see if a clause is implied by the knowledge base. Now, if your knowledge base is in prime implicate form, then checking whether a certain clause is implied by this guy, remember this guy is in PI form, is just a matter of checking whether any of these clauses is a subset of this. So if a clause in delta is a subset of alpha, then of course we know that it's implied. If no clause of delta is a subset of this, you know for sure that alpha doesn't follow. So now causal entailment, which is generally a hard query, becomes easy in this particular case. Now there is one more application for this prime implicate form. Remember what was the procedure for existentially quantifying variables from a CNF? We said what you need to do in that case, if you want to existentially quantify a variable, then go ahead and do all possible resolutions on that variable, and then throw out the clauses that mention the variable. Well, in this case, if you have a PI form, then I already closed under resolution. So if you want to actually existentially quantify a variable, let's say D, all you have to do is drop the clauses that mention D. That would be 1, 2, and 3, and that's good. So existential quantification and causal entailment are two things that are actually easy on this PI representation. And we'll go in a little bit and talk about the dual part, which is prime implicants, which, as I said, is going to be more relevant for us. And then you'll see that they're actually, these are dual notions. This is basically the notion of prime implicant. Okay, and in your paper, we refer to this as IP. And again, realize the difference is just in the last thing, implicant versus implicant. So the situation is symmetric in this particular case. And what we want to do is basically initially define an implicant of a knowledge base. And this is, as you can imagine, this is basically a term T such that T implies the knowledge base. All right. So if I have my delta as, let's say, A and B, or not B and C, you will find in this case that this term, which happens to be A and C, is an implicant. So this is an implicant, right? So this is an example. And let me just give the definition of a prime implicant. And basically, as you would expect, this is an implicant that is not subsumed by any other implicant. All right, that's basically the definition. And if we continue with our example, what does that mean? This is an implicant. This implies that. So in the sense that if you set A to true and set A to and set C to true, you have satisfied this formula. All right, you may be able to see it or not, but that is the case. This basically implies that. T in this case implies delta. The question is, so this is an implicant. The question, is it a prime implicant? Right? Now, for it to be a prime implicant, this should stop being the case if I drop C or if I drop A, for example. And in this case, if you drop C and just say A will no longer imply that guy. Setting A to true doesn't satisfy this formula. Similarly, setting C to true alone doesn't satisfy this formula. So in fact, in this case, it is prime. Now, let me ask you a question. Let's go ahead and say that T is A and C and not B. Question, is this an implicant? Is this an implicant of that? Does it satisfy the formula? Yes, it does satisfy the formula. If I set variables as such, that satisfy this formula. So that makes it an implicant. The question, is it prime in this case? Is it a prime implicant? Remember, for it to be a prime implicant, if I shorten it, it stops being an implicant, and people are saying no. Exactly, it's not prime because I can get rid of this and that will remain to be an implicant. So there is a shorter implicant. All right, so this is not prime. Okay, we're getting here to the punchline, and as far as understanding what these guys are, and now you see what their importance. One way to think of prime implicant, and you need to remember this because it's going to come up next time when we talk about explainability. If I give you a Boolean formula, an implicant, you can think of it as a minimal way of satisfying the formula. That is a minimal variable setting that satisfies the formula. The fact that it's an implicant means that variable setting does satisfy the formula. The fact that it's prime means you cannot make it any simpler, right? Every variable instantiation in that implicant is necessary to satisfy the formula. And that ends up being at the heart of answering why questions. Why was something the case, right? That ends up playing a role there, and you'll see it more vividly with examples later. But let's end this example or this part of the discussion with the PI or IP representation. And this is basically where we have IP form, just like we had PI form. And this is basically represent a knowledge base delta as a disjunction of all its prime implicants, right? So what you need to do in this case is you take your knowledge base and find all minimal terms that satisfy it, right? And then you put them in one big disjunction. So you would go ahead and do T1 or T2 or Tn. Each one of these satisfies the formula. And moreover, it does it in a minimal way. You cannot make it any shorter. If you make it any shorter, it will stop implying this guy. You collect all of these guys and put them in one big disjunction, and you end up getting what we call the IP form. It's a very important representation. You'll be surprised. So I'll tell you one thing right now, and maybe so that you try to remember this. When we talk about explainability next time, we're going to talk about this notion of bias, for example. Is a decision biased? Right? Sometimes you have a classifier and the classifier is making a decision. Let's say the classifier is trying to admit people to a program. And you may have what we call protected features, are features that are not supposed to be made in a decision. Sometimes people would talk about the classifier being biased. We'll make a finer distinction. We're going to talk about whether a particular decision is biased, because as we'll see, it is possible that the classifier is generally biased, but a particular decision it made may not have been biased. And we'll see that one way to define bias is to say, did that decision depend on protected features? Were the value of protected features in the instance essential for the decision it made? And you'll find that the answer to that comes from understanding a property of prime implicants. They'll end up playing a role in detecting whether a decision is biased or not. What you need to understand, and why these two representations are received so much attention, is their kind of canonical forms that reveal the logical content of a knowledge base in a particular way. And let me again focus on this guy in particular. This guy is writing down all possible ways you can satisfy the formula, all possible reasons why the formula may be true. And each one of these reasons is minimal. And because of this property, you can use it to do a lot of things, as we will see later. Let me just end here with a couple of remarks on the relations between these guys, prime implicants and prime implicates, because they're basically dual. And the first thing that I want to say is that if you have, and let me start with a clean page here. If you have alpha as prime implicate of a knowledge base delta, then this is if and only if not alpha is a prime implicant of not delta. Okay, so you've got this first duality here. And the other thing that I want to mention about these guys is the relative sizes. Right? One thing that we talked about is when I come up with a new representation, like I say, go ahead and represent your knowledge base as a set of prime implicates or as a set of prime implicants. What do I expect in terms of size? And in this case, we want to try to contrast these two guys. Is one of them more efficient representation than the other? And remember, this is the prime implicates, and this is the prime implicant. Let's say how much is your memory. If I'm going to put this guy here as a subset of something, is it a subset of CNF or DNF? In what form is this? This is prime implicate. These are clauses. So this is actually a type of a CNF. And this is actually a type of DNF. Very good, guys. Thank you. Remember, prime implicates are in CNF form, prime implicants are DNF. Okay, so people are saying these are, they should be of similar sizes. And I would give you now an example that actually shows they're not comparable, meaning it is possible that you would have a polynomial number of prime implicates but an exponential number of prime implicants, and or the other way around. You could have a polynomial number of these guys for a particular knowledge base, but an exponential number of these. So in general, they are not comparable. And the kind of canonical example people use for this is this formula, which is this. It is parameterized by n, so you can make it as big as you want. So I'm going here from this to n minus 1. And what I'm doing here is x2i or x2i plus 1. Okay, so is this, what form is this in? Is this CNF or DNF? This is a clause, and I'm taking conjunction of clauses. So as people are saying, it is indeed CNF in this case. Let's take an example of this guy here on the side, where basically we're using n equals 3, I believe. And this would be x sub 0 or x1 and x2 or x3 or x4 or x5. So this is now to help you visualize what's going on beyond the indexing. So you can make n as big as you want, but let's say this is basically one version of this. Okay, so this is a CNF. Let me ask you, is this in prime implicate form? Is this guy in prime implicate form? And in principle, you should be able to conclude, and somebody's saying yes. And what is the argument in that case? Why is this already in a prime implicate form? So none of the clauses subsumes the others. This is one condition, but that's not enough. Exactly. Someone is saying, I cannot do any resolutions. Remember the procedure for obtaining prime implicates. Close under resolution and remove subsumed clauses. Well, there's nothing can be done here as far as resolution. Why? Every variable is appearing positively. There is no applications of resolution, and there is no redundant clauses. This is already a prime implicate form. So for this formula, the number of prime implicates is basically polynomial. Now, if you try to find the prime implicants of that guy, you're gonna get it blow up. All right. In fact, so for this guy, poly number of prime implicates, but this guy will actually end up having 2 to the n prime implicants. And you can guess what these will be, right? What do you need to do to satisfy this formula? You need to satisfy one of these and one of these and one of these. So your prime implicants end up being something like, okay, x0, x2, x4, but then I can do x1, x2, x4, and all of the other combinations. And none of these guys can be shortened. There is no way to satisfy this without satisfying one of each of these clauses. This should be actually this guy here, and you can see what's going on. So I had a polynomial number of prime implicates, but an exponential number of prime implicants. And if you take the negation of this formula, you will find the opposite for the negation. And you can convince yourself with that. So the negation of this formula shows the opposite, shows if that would be a formula that has a polynomial number of prime implicants, but will have an exponential number of prime implicates. All right, guys, we're done with our discussion of this part. When we come back after the break, we will end up talking about diagnosis, and it will be a more concrete discussion. So I will see you at 11.